Good morning everyone. My name is Dolly Singh and today I will be representing on the topic shading and its type as part of our computer graphics and visualization course. So let's get started. Here's a quick look at everything we will cover today. We will begin with an introduction to shading, understand why it matters, then move into the illumination model and how light behaves on surface. After that, we will deep dive into the three main shading techniques: flat, gorgot, and foam, compare them, and finally look at advanced methods and real world applications. By the end of this presentation, you should be able to understand the role of shading in 3D graphics, explain how light interacts with surface, clearly differentiate between flat, gorgot and foam shading, follow the math behind each technique, evaluate trade-offs between them and connect all of this to real world scenarios. So, what exactly is shading? Shading is the process of determining the color and intensity of each pixel on a 3D object to simulate realistic lighting. Without shading, every surface of a 3D model would just look like a flat, featureless polygon. There did be no sense of depth or dimension. Shading gives us the illusion of depth, shape, texture, and material properties. It's a core step in the rendering pipeline. We go from geometry to rasterization to shading and finally to the output we see on screen. The key question shading answer is how does light interact with a surface to produce a perceived color. Why does shading matter so much? First, it brings realism. It makes 3D object look physical, believable. Second, it helps with depth perception. Gradual color changes let us judge how far our curved a surface is. Third, it helps with material identification. We can tell whether something is matte, metallic, or glass just by how it shaded. Shading is used everywhere: video games, animated films, medical imaging, CAD, CAM, and virtual reality. A perfect example is Sphere, where with flat shading just look like a 2D circle, but with proper shading, it immediately reads as a 3D ball. That's how powerful the shading is. Now let's talk about how we model light mathematically. An illumination model defines how light reflects from a surface. There are four types of light sources we commonly use. A point emits equally in all directions like a light bulb. A directional light sends parallel rays like sunlight. A spotlight is cone shaped like a flashlight, and ambient light is uniform background light with no specific direction. The most widely used model is the foam illumination model, given by the equation given we will see in the PPT. This equation has three parts: ambient, diffuse, and specular, which we will look at next. Let's break down these three components. First, ambient reflection. This is a constant background light. Even in shadow, objects are slightly visible. Formula we will see in this, an example also. Second, diffusion reflection. This is a light scattered equally in all directions from a rough surface. It's based on Lambert's cosine law. We will see it on the PPT. Third, specular reflection. This is the shiny highlight you will see on polished surface formula. Formula we can see on the PPT. A higher shining component N gives a smaller, sharper highlighted with the given value we get about 0.35. Together, these three components make up the total illumination at any surface point. Flat constant shading. Now we come to the first shading model, flat or constant shading. The idea is simple: compute a single intensity value for the entire polygon face and fill it uniformly with the color. The algorithm is calculated the surface normal and compute the illumination I and fill the entire polygon with that one color value. This assume the light source and viewers are both far away, which specify the math. We have few advantages. It's extremely fast and very easy to implement. It's best suited for flat faced object like cubes, pyramids, or quick wireframe previews. Quick numerical example also we can see in the PPT. Next is God shading, developed by Henry God in 1971. Instead of one color per polygon, we compute lighting at each vertex and interpolate the intensity across the polygon. We can see few steps, advantages and disadvantages in the PPT. Here is a quick numerical walkthrough. Say we have a triangle and vertex intensity, and let's we can see it on the PPT. Now we have form shading. The most advanced of the three is form shading, developed by Python Kong in 1975. The key difference here, instead of interpolating intensity values, we interpolate the surface normal vectors across the polygon and then compute the full lightning model at every single pixel. We have few steps in this, which is compute vertex normal, interpolate them across edge, and scan lines, normalize the interpolated normal at each pixel, then apply the full form illumination formula. Here we can see a numerical on foam shading. Here is a comparison table that we can see. Ray tracing is completely different approach. Instead of rasterization polygon, we can raise from the view's eyes through each pixel into the scene. At each intersection, we compute shading and spawn additional rays for reflection and reflection. It naturally supports shadows, reflection, and reflections at the cost of heavy computation. In practice, shading is implemented using GPU shader program writer in GLSL, OpenGL shading language. The vertex shading runs per vertex and handles the transformation. Shading has application across virtually every visual computing domain, from video game engines like Unity, Unreal to Pixar's path-traced animated films to medical imaging for CT and MRI scan to VR, AR, CAD software, automated design, reviews, architecture walkthrough, and even scientific simulation of weather and fluid dynamics. To summarize, shading determines how color and light appear on 3D surface. The Phong illumination model combines ambient, diffuse, and specular components. Flat shading is first but coarse. Gorgot shading is something but smooth but can miss highlights. Phong shading is the most accurate advanced technique, including doing Phong, cell shading, bump mapping, and ray tracing. Ultimately, the right choice depends on balancing visual quality and performance requirements. For those who want to explore further, I have listed some excellent books and online resources on the slide, including the freely available physical based rendering book and learnopengl.com. I did like to thank Mr. Shivshankar Rajput, faculty at Agropolis Institute, for guiding this presentation. Thank you all for your time and attention. I am happy to take any questions.